Okie dokie. So Dr. Modestou uses clumped isotopes of carbonates to determine past temperature at Earth's surface and at depth, as well as process temperatures within other planetary bodies. She also works with radiogenic and cosmogenic isotopes in the context of paleoceanography to study events in Earth's history. Sevi undertook her PhD at the University of Glasgow, looking at the application of radiogenic and cosmogenic isotopes to infer information about the state of the Mediterranean climate and its connections to the Atlantic throughout the latest Miocene. After a postdoc in Glasgow, looking at clumped isotopes in fossil carbonates, she moved to Bergen, where she continued this line of research, generating Middle Miocene temperature records on longer timescales. Since December 2021, Dr. Modestou works as manager of the NICEST lab, that is the Northumbria Isotope and Clump Geothermometry for Environmental Studies Lab. Quite a mouthful, NICEST. Ongoing projects include developing a method to apply seawater lead isotopes preserved in sediments to improve astronomical tuning and geochronometry in the Mediterranean, and working with the COVID-delayed IODP Expedition 395 to unravel tectonic and climatic controls on the evolution of North Atlantic deep water formation, amongst other things. So we're very pleased to be able to welcome Dr. Sevi Modestou to give today's Paleoclimate Society seminar. Thanks for joining us, Sevi. I'll now pass over to you.
Thanks for that introduction. It's really nice to be invited, and I really appreciate the opportunity. I have to admit that I have changed my title. So my intended talk was this one that was advertised, and I've kept it mostly the same, but I just found that when I was preparing, it was really difficult to really give you a full view of the state of the art when it comes to the MSc, because there's a lot of detail that we just can't cover in 30 minutes. So the talk will still talk about the Messinian salinity crisis, but this title might be a little bit more accurate for what we're really going to talk to in the end. So I'll start off with some key facts about the Messinian salinity crisis. Geologically speaking, it's a pretty short event, actually, and it is the result of gateway restriction through the Gibraltar region. So prior to the MSc, there were multiple connections across North Africa and southern Spain, connecting the Atlantic to the Mediterranean. And due to the rotation and movement of the African plate relative to Europe, those gateways became progressively restricted, leading up to a situation in which the mid-latitude now isolated Mediterranean basin, which is evaporation dominated, hydrologically speaking, was then able to precipitate evaporates. There are 4 major units. They start with stratigraphic order, the lower primary evaporates, lower evaporates, which are mainly gypsums found high up on the margins. And next in terms of time is the halite. These are thick units that are only found in the deep basins. And then we have the upper evaporates, which again are made primarily of gypsums. There are also some other things in there. And then this is all capped by the brackish water. So we go from hypersaline to hyposaline. We get these brackish water deposits called the lagomari on top. Now, when you look at the evaporite deposits in terms of volumes, the numbers are actually really staggering. It's one of those questions where it's difficult to really comprehend the volumes that we're talking about. So some of the deep basins are estimated to host up to 2 kilometers thick halite units. The entirety of the evaporites themselves have been estimated at over 1 million cubic kilometers. This is a lot of salt that has been sequestered. This is a very extreme event, and a lot was going on in those relatively short 640,000 years. In that time, based on these estimates for volumes of the evaporites, that's about 6% of the salt in the global oceans. So if you think in your mind, comparing the volume of the global oceans relative to the volume of the Mediterranean, you're taking a lot of salt out of the global oceans and depositing it, sequestering it into the Med. Here is an image of what some of those deposits look like. So if you've never had the privilege of being able to see them in person, I really recommend it. I have one Johanna Lofi down at the bottom here. She's about 1.7 meters tall, and behind her are just 4, 1, 2, 3, and 4 at the top, gypsum cycles out of many, many gypsum cycles of the lower evaporites. So it gives you a kind of understanding of the scale that we're talking about. So during the deposition of the first stage, so these primary evaporates in the first, the lower unit, pretty much everyone is in agreement. Probably the basin was still quite deep because of the position of these deposits up high on the margins. And there's a lot of evidence for coeval initiation of the salinity crisis right across the basin. But after this stage, so for the halite and later stages, there's a lot of disagreement. There's a lot of controversy in the literature, and these two images sort of illustrate the two camps. One camp is of the thought that most of the basins were completely desiccated, resulting in like small hypersaline lakes dotted across the basin. The other camp, which is the deep water evaporate formation model, believes that actually all the way through, we probably had the basin completely full of water, which is really counterintuitive to the classical way of thinking about the MSC, because classically you think, okay, you put some salt water, you dry it out, and that's how you get your evaporate deposition. But actually, as I'll show you with a few examples, there's evidence that that was not the case. So arguments for the desiccation model are mainly centered around a really large body of seismic evidence and the interpretation of that evidence, including images that are interpreted as deep fluvial incisions, mega flood deposits, and a really extensive and important seismic reflector that is called the MES, or the Messinian erosional surface, which can be found really all the way across the basin. And there's some isotope geochemistry as well that I'll show an example for later. Arguments for the deep water formation model include, as I mentioned, the coeval start, which is really consensus at this point for the first unit anyway. But then beyond that, these really massive volumes of salt that you have are really difficult to form if you were to just close the gateway and just dry the med down. If you do that just once, you get something in the order of like 6 to 10, maybe a few tens at the most meters of evaporates. That's nothing near the thousands of meters that we actually have. So the difference, it can only be explained by repetitive or continuous resupply of salt, which has to have come from the Atlantic. If you look at the geochemistry of the evaporate deposits from disparate locations, the strontium isotopes, for example, are very similar, and other geochemical signatures are very similar, suggesting that they were evaporated, precipitated from a similar parent brine, which you wouldn't necessarily have if you had a lot of different dislocated basins. And there's also some faunal arguments that I'll show you in a moment. So those are the main arguments, and I'll just give a couple of brief examples of what that evidence looks like in the literature. So obviously we can't go through everything, we just don't have the time, but I've just picked a couple of examples. This is an example of what the seismic evidence looks like. So this green line is interpreted as the Messinian erosive erosional surface. This is that basin-wide erosive feature that is found on seismics of this, showing these this time period. Above it, you've got Pleistocene sediments, and then in this erosive surface, you'll find that you've eroded down into the layers below, which are Messinian and Tortonian in age, or at least interpreted as. And this particular example shows these fluvial incisions really nicely. So this seismic profile was taken just offshore from where the Ebro enters the Mediterranean. And so the authors are saying, look, for you to have fluvial incision, you must have had a major sea level drawdown for the Ebro to have been able to erode this far down into the basin. And to have this Messinian erosional surface appear everywhere, that drawdown must have been everywhere. So that's generally speaking how the seismic evidence logic goes. From the other side of the story, this is an example of the faunal evidence. from the latest phase, the Lagomare phase. And what Stoica et al. Did was they took samples from the Paratethys, which is today the Black Sea, Caspian Seas are remnants of the Paratethys. Again, the connections between the Paratethys and the Mediterranean, not super well understood. But they took samples from here, they took samples from southern Spain, they looked at the ostracods, and they found that actually there's a bunch of species that are endemic only to the Paratethys that were found all the way across the Med in the Lagomare phase, those authors then show in this sort of cross section, okay, logically speaking, if you've got these bugs over here, in order for them to get all the way across all of the sills in between, the water level had to have been high enough for them to get from one place to the other. Another really recent study that shows the geochemistry, geochemical evidence and arguments really nicely is this one from Aryan Growth et al. From a couple of years ago. I mentioned strontium isotopes are a key argument. They're key evidence used. The global ocean curve for 87, 86 strontium is shown in the back in blue. And we've got this purple line, which shows the evolution of strontium isotopes in the Med during the MSC. So the lower evaporates, the halite phase, and then the upper evaporates in Lagomare. These gray dots are from several studies. This is a massive compilation from many studies over time. And we tend to always get similar shapes. The data tends to compile together, gives these similar shapes where we've got some kind of values that are slowly coming away from the seawater curve a little bit before the MSC proper. And then we've got values that are slowly coming away even more. And then all of a sudden we have this drastic change. So generally this has been argued in the past as representing, a complete restriction from the Atlantic, and then the strontium signature is being imparted from local sources like, for example, the Rhone River. But what these authors argue is actually, if you look at the Paratethys strontium and you model those, you look at those through time, and you can think about it as maybe a mixing or dilution of fresh water actually coming into the Med from the Paratethys, which probably also requires water levels to be high to have that connection as well. You could explain these values from mixing with the Paratethys, and they took it a step further, and they looked at the chemistry that's expected for waters coming from the Paratethys, mixing with the chemistry expected for Mediterranean waters. And they actually found that you could have gypsum formation, gypsum precipitation, much lower salinities than are commonly expected to be required. So something like 40, 50 PSU, you've got gypsum formation possible, as opposed to 120, 140 PSU, which is a really big difference, and gives you a mechanism for being able to form these evaporates in essentially what is a very deep basin with potentially quite low salinities. A few arguments against in either case. So starting with the desiccated model, there could be alternative explanations for the evidence that the reflectors that people are seeing in seismics. There's not a lot of direct confirmation for some of the deposits. So there's deposits that are interpreted as mega flood deposits, but we don't have direct samples to confirm what those deposits really are. It's very difficult to constrain erosive surfaces in time. And the geochemistry doesn't actually completely negate Atlantic input. So even if you didn't have, say, this from the Paratethys or from rivers, you can have some, relatively normal marine conditions and restrict the gateway. As long as you've got something less than about 25% or so Atlantic inflow, you can start to evolve strontium isotope compositions in the Med that are different. So you can still have a little bit of a connection, a little bit of water coming in from the Atlantic and get those compositions. In terms of the deep basin model, the main arguments against it, in addition to the vast body of seismic evidence that we've just barely touched upon here, there's also some major problems in terms of we don't know where the gateway was. We really have no idea, as I'll show you in a moment. And we don't understand how that gateway could have worked. So if you model gateway dynamics in terms of what fluvial erosion does, it's really difficult to sustain a small channel connecting the Atlantic to the Mediterranean for a long time without that channel eroding and becoming bigger. And if you get too big, then you enable outflow, which, as we'll see in a moment, would be a problem because you can't build up this extreme salinities to allow you to deposit salt, or at least that's sort of the way that the arguments go. So it's a bit of a catch-22, and we need to keep working on this, and potentially looking at the gateway and understanding that better is one way of going to maybe find a resolution to this disagreement that's persisted for a really long time. One recent paper that looked at exactly this is from about Kreigsman and co-authors, and they compiled all of the data that exists for the gateways. And essentially their conclusion is that where we don't have data at all, which is in the Strait of Gibraltar, is probably actually the most likely candidate for the persisting connection. So we really need to get looking at that. Now, I just would like to take a bit of a step back and explain why this gateway exchange, where it comes from, how it works, and why it's important. So probably lots of you guys are familiar with the concept of sapropels that are deposited during the wetter phase of the precession cycle in the Mediterranean. Really, we want to focus on the majority of the rest of the cycle with this type of circulation, which is kind of it's more similar to modern circulation mode in the Mediterranean. Because evaporation rules for the most time at mid-latitude locations, in terms of the hydrologic budget, we get a lot of evaporation over the basin. That freshwater loss is going to be compensated by inflow coming in from the Mediterranean, but it's also causing high salinity water, higher density, higher salinity waters to be formed. Those will be advected down, oxygenate the deep waters, which gives us sort of the normal marine sedimentation. But it also drives outflow here because of the density difference. So you've got Atlantic water that's fresher. You're developing this higher, more saline, higher salinity, higher density Mediterranean water, and that density difference is actually driving the majority of outflow. So estimates are quite like conservative estimates between about 0.03 and 0.1 spare drops for the total of evaporation. Whereas inflow is actually 0.8. So most of that has to actually be made up by the density contrast that's driving this exchange. And it's this dynamic here that causes a problem when we want to say we had a connection and the basin was full, but we didn't have outflow in order for us to keep that salt in the med to precipitate these evaporates. This is where the problem comes in. So the other thing that's important to note about this gateway exchange, it also means that we are exporting signals that are generated within the Med due to the specific regional climate that affects the Mediterranean into the North Atlantic. And a lot of people have posited that this denser, more salty water is an important preconditioning element for North Atlantic deep water formation. Modern hydrographic data are maybe a little bit inconclusive. You've got evidence going either way, but certainly in the paleo records, we can see in the Pleistocene, and I'll show an example of that in a moment, of some teleconnections. As this denser water mass flows out of Gibraltar, it flows out at sort of subsurface to intermediate depths. And some of it flows south, some of it flows towards the west, but the majority of it flows up towards the north into the North Atlantic. Yeah, so there's your kind of modern overview of how it works. And that allows us to hypothesize that there can be important teleconnections that are linking the impacts derived from the Med to the outside. One example that I chose to illustrate this, which I think is a really nice study by Stephanie Capeth-Barr et al. From 2021, so just last year, Essentially, they're hypothesizing that this salinity driver can actually cause sea surface temperature increases in the North Atlantic, which has also been seen in some modeling previously. Basically, what those authors noticed is that the CO2 record is showing some decreases, but at site 982, when we've got decreasing CO2, which you would expect to go hand in hand with decreasing temperatures, we actually have increases in the sea surface temperatures at site 982. And what they found, in addition, from sites more proximal to the Med, so here's the map, 982 is in the North Atlantic. The other sites that they looked like are much more proximal, are much more proximal. So they could use some of their characteristics as a salinity proxy. And what they find is that particularly in this event centering around 2.8, this really strong SST increase is associated with a very strong salinity increase in Mediterranean outflow. And so what they're saying is, as Mediterranean outflow exits, if you look at a depth transect across the North Atlantic, what you see is the Mediterranean outflow shoaling as it gets to the moves northwards. If you were to increase the vigor of flow, then you could potentially increase this heat transport, like a heat channel directing the spraying heat out of the Med and towards the North Atlantic. So I think that's an interesting study, and something that would definitely help to explain why there's a delayed increase in North Atlantic, in glaciations around the area, when you see CO2 levels dropping, but you have this evidence of sea surface temperatures rising instead. So, okay, if we have examples from the Paleocene, and there are, of course, other studies that show similar examples, if we see that for what is, relatively speaking, a minor change in salinity, what about the impact of this major change in salinity, which is the Messinian salinity crisis outside of the Med? And there aren't really well-known, really obvious examples of things from the North Atlantic fighting with the Messinian salinity crisis. So where should we be looking, and when should we be looking for that? And that's a question that was tackled in this study from both our Capella and co-authors. Essentially, this study, if you're familiar with Tim Herbert et al.'s paper from 2016 in Nature Geoscience, where they compiled sea surface temperature records from across the globe, they found this late Miocene cooling, and they show that there's temporal correlation between minor initiation of glaciation, sort of relatively minor, at least compared to glacial maxima. Evidence for the northern hemisphere was trying to start glaciating. And what Capella and co-authors did was they said, okay, if we're seeing a cooling in sea surface temperatures, is there any way that we could relate that to what's happening at the gateways? And if you remember, prior to the MSC, we have this ongoing restriction where the gateways are closing. And because the exchange is primarily driven by the density contrast, as you make the dimensions of that gateway smaller, you're going to cause more vigorous flow, because you need to exchange the same amounts of water, but you have a smaller cross section to do it in. And so that's what this figure in panel D is showing, that as you restrict those gateways, the forces at play are going to cause you to have higher flow velocities. You're going to have more water entrained because of it. As you increase the vigor of the the Mediterranean outflow into the Atlantic, you're also going to be increasing entrainment. And these effects are coincident with different factors that are seen outside of the Med. For example, strengthening of Arctic overflows, increased activity of glaciation on Greenland, and they are temporally coincident with this drop in sea surface temperatures that Herbert et al. Showed. So maybe what we've been missing is actually we're looking in the wrong place. Maybe we should be looking slightly before the Messinian salinity crisis. Okay, and now here is where I'm going to ask the audience for their help. So another approach that you can use is to look at evidence from just outside the gateway on the Atlantic side to try to understand gateway dynamics and changes in the gateway. And that's what I tried to do as part of my PhD thesis. This is data that I've been sitting on for a little while, and the reason why will become apparent in a moment. I looked at crust 3514-6, which is a ferromanganese crust deposited on the Lion Seamount at a relatively shallow water depth consistent with the modern Mediterranean outflow plume. So spatially it's in the right place to record what we want it to record. And I'll be comparing it to some other crusts from deeper in the water column, but from the same region, as well as this crust here, 121 DK, which is from far enough away that we would expect it wouldn't be impacted directly by Mediterranean outflow. So lots of crusts, lots of records. I will build up this figure slowly so that hopefully everybody can follow me. Starting with the pre-existing data from these crusts, so 65 GTV, also from the Lion Seamount, but from much lower down in the water column. The Tropic Seamount crust record, the pre-existing one is here, and so on. What you can immediately take from these records, because they were using wet-based chemistry, they just don't have the temporal resolution to resolve an event as short as the MSC. Granted, they were never necessarily trying to. They were more interested in long-term records. But if we want to extract information specific to the MSC, these records just don't have the temporal resolution to do it. So we need to look at this using a different method. And I use laser ablation for the temporal resolution you can get. So here is my record from 3514-6. Superimposed over the top. And we do get the temporal resolution. And actually, we do see some things potentially happening here, which is pretty interesting. One more record that I'd like to compare to is this composite crust record from the same position as 121 DK. So it's also from the Tropic Seamount. But it's actually taken from, this is a composite record of multiple crusts that were recovered across the depth profile of the entire seamount. There are pros and cons to using the composite, but in this case, for this part of the record, I think it doesn't really matter because almost all of the crusts for this time period show essentially the same thing. And so when you compare all of these things, you can see that there's some relatively high frequency events happening in the 3514-6 crust. You don't see these events in the Tropic Seamount crust. So it's highly likely that this is a signal coming from changes in Mediterranean outflow. But what exactly it means beyond that, that's where things get a little bit tricky. So I'm going to put a pin in that. And I'm going to quickly jump to some lead isotope data that I collected from within the Med. So these are records that are from bulk sediment leachates from marginal basins that were located at disparate locations across the Med, as shown in the map. So we've got southern Spain. I can't move, sorry, I can't move the bar that's showing people for whatever reason. So this map is a little bit difficult for me to get to. I can't actually see it. Hopefully my cursor will go to the right place. So we've got the Sorbas Basin in southern Spain. Around here, we've got Sicily in the central Med, and then the northern Apennine pretty in northern Italy. And these are the records. So there's a lot of interesting stuff in these records that I don't have time to talk about. If you want more information, please go to see my paper, or we can chat about it afterwards. But I just wanted to show you that there is some data. This is the only data we have to compare with for inside the Med that could maybe help us understand what the Mediterranean outflow value should have been. And if I plot them in a more simplified way, at first glance, it looks like maybe doesn't actually help us very much when we compare the range of compositions for the equivalent time period from the crust to what we're getting at these marginal sites. But if we look at it in a little bit more detail, actually, maybe it does help us. So we can probably ignore these compositions because they're from a marginal basin that's very far away from where the exchange is happening. And when we look at the compositions in time, we find that actually the majority of them sit close to this crust value, because those excursions are only very short-lived events, and most of the time we're sitting closer to this value. So actually, that might be a reasonable, this pre-MSC value that's relatively stable might actually be a reasonable approximation for the lead isotope value of Mediterranean outflow. So that's useful and helpful. And that helps us get somewhere. But then there's one more aspect to this record that we have to consider, which confounds things a little bit. And that is the beryllium isotope data. So normally the age model for these crusts is derived through the 10:9 beryllium ratio. And when I tried to do that for this crust, I found that the 10:9 ratio ages in some cases seem to be reversed. And there's no physical evidence in the section of crust for, sections of it to have somehow flipped upside down. So we should be able to be pretty safe in the assumption that the samples through the crust are actually in stratigraphic order. So these apparent reversals in age are an artifact of something else. And so I plotted the 10 and 9 concentrations separately. And what you see is that you do have variation in the values, which we could potentially argue is linked to changes in the exchange, because in the Atlantic, we actually have a lower 9 beryllium concentration than in the Mediterranean. The problem is that the relationship we're seeing looks like it's reversed. So if the Mediterranean 9 beryllium concentration is high and we expect to then have less of that water coming through, we would have expected this value to be down here instead of going down instead of up, basically. So it's complicated, and I'm still working through this data and trying to understand it, and I would love any input anyone out in the audience might have for me. So in summary, I hope that I have convinced you that the Mediterranean is a really important basin for paleoclimate research, including beyond just trying to solve this major controversy, but also looking at teleconnections and the export of climate signals outside of the Med. It's been more than 50 years since the deep desiccation model was first posited, and we're still arguing about these things. We've got to find a solution at some point. And I think one of the major things that's missing that we really need to do, especially for that particular part of this problem, is more complete drilling of the deep deposits. So essentially, we haven't recovered the deep deposits for various reasons, including safety. And so I wanted to give a little shout to the image drilling proposal, which is one of their objectives is to do just that. And that's it for me. I open the floor to any questions, and thanks again for everyone for listening.